Hello, everyone. Hello, everyone. Can you hear me? Yes. It is my pleasure this morning to introduce Professor Judy Holdener. After receiving a bachelor's degree in mathematics from Kent State University, Judy completed her PhD in algebraic K-theory at the University of Illinois. She began her academic career at the U.S. Air Force Academy before coming to Kenyon College, where she is currently a professor of mathematics. Judy is a renowned educator, and it's fair to say that she is fully immersed in the craft of teaching mathematics. She received an Outstanding Teacher Award as a graduate student in Illinois. She was Instructor of the Year in Mathematics at the Air Force Academy, and since arriving at Kenyon, she won a Junior Teaching Award. She held the John B. McCoy Distinguished Teaching Chair, and she won the Mathematical Association of America's Ohio Section Teaching Award. Judy's research interests are broad, ranging from algebraic topology to number theory to iterative balloon twisting. Judy has made numerous contributions in her publications, and significantly, she has found a way to include undergraduate students in much of her research. We are honored to have her with us this morning. Won't you please help me introduce Judy Holdener?
Thank you, Bruce, for that very nice introduction. And I want to thank Bridges and the organizers. I think it's on. The testing. Oh, maybe it's just flipped a little bit. Here, let me move it up. I want to thank the organizers, too, for giving me this opportunity to speak at length about my mathematics that appears in my artwork. I'm going to be talking about this piece here that I created last year. It actually marks my... Okay, let's see. I gotta somehow get it not to flip. Is that better? Maybe not. I'm not wearing the right outfit. I wore it to match my art. I wasn't thinking about this. Let me try the other side. Is that better? Okay. Okay, so I created this piece last summer, and it marks my first, use of digital art in my work. In the past, I've been using painting and drawing. I started out as an art major as an undergraduate and switched into the major in mathematics in my junior year. I decided I couldn't stop taking math. This piece was created in Adobe Illustrator. I also used Mathematica and Maple to produce some of the patterns that you see, and I used Photoshop to manipulate some of the images to get some of the effects that I wanted. I titled the piece Immersion, and for the next, say, 45, 50 minutes, we're going to all be immersed in it. Okay, so in this piece, what I do is I focus on the notion of immersion from two different points of view. In the first part of my talk, which will be the bulk of the talk, I'm going to focus on the vernacular. What I'm going to do is talk about some of the patterns that you see in the piece that reflect my own personal immersion in the world of mathematics, an immersion that arises from my day-to-day work as a professor of mathematics. And then in the last portion of my talk, I'm going to talk about the formal definition of immersion, because it turns out that the formal definition is what defines the composition of my piece. Okay, but first I want to tell you my favorite immersion story. So this is a story about me. I was traveling. I was coming back from a math conference in DC. And I wanted to fly from DC to Columbus, and I noticed that there was an earlier flight that I could take. So I arrived early at the airport and asked if I could get on the earlier flight. And when I got there, this is what I saw. Okay, it's not good. This isn't actually the picture I took, but this is pretty much the kind of thing that I saw. And so I went up to the desk and said, can I get on the earlier flight? And the person behind the desk said, absolutely not. There's a waiting list. In fact, we have to bump some people. And so I said, well, that's fine with me. I can just go to Starbucks and get myself a cup of coffee and get to work. So I eventually found a seat and started working away, having a grand old time until, I don't know how much time passed, but I woke up when the person who I had spoken to earlier behind the desk, her face was like this far away from mine. I was seated, she was squatting down like this, and she was screaming in my face, "Flight 479, boarding!" Like that. And then I just woke up, and I looked up, and there's what I saw. It was like totally empty, except me. And she said, everybody's on the plane except you. And I'm like, oh, I'm so sorry. I pack up my stuff, get on the plane. Later told my family the story, and they said, well, she was so mean. I said, no, she was not mean at all. This was exactly what I needed. And if she didn't do that, I would not have made my flight, right? I mean, for me, I can immerse myself in my work. I don't care how many people are around me. The rest of the world disappears. And I actually think that's a really good thing. I'm sure some of you have the same sort of habits. The downside, though, is that as mathematicians, when we do that, people will see us as either A, zoned out, which is accurate. I'll go along with that one. Or B, absent-minded. I don't really like absent-minded because I don't think it's right to say that our mind is empty. But in any case, one thing I'm hoping to do with my artwork is to reveal this mathematical world that I get immersed in to a wider audience so that they can understand that really my mind isn't completely empty. I am thinking of something. Well, of course, sometimes I don't know what I'm thinking about, to be honest. I just sort of disappear, and when I come back, I'm like, I don't know where I was. So my goal here is to make the mathematical world visible to a wider audience. Okay, so as a professor of mathematics at a small liberal arts college, student learning is my #1 priority. And so many of the patterns in my piece reflect the courses that I teach, the content of the course I teach. I teach multivariable calculus nearly every year. In fact, I'll be teaching it in 15 days, which is a little bit scary. And so I include some patterns that reflect that course with gradient fields and contour diagrams and normal vectors appearing here. I also teach abstract algebra fairly regularly, so I've included some patterns that have nice symmetries. Of course, I would have included those anyway just because they're beautiful, but I like to think of them as representing abstract algebra since abstract algebra contains the tools that we use to quantify symmetries. I've highlighted a wallpaper pattern here, which is a pattern that has translational symmetries in 2 different directions. And in other places in the artwork, there's also wallpaper patterns that I've then transformed in some way. So I guess technically you wouldn't think of them as wallpaper patterns anymore, but they started out as one. I also like to teach number theory. It's one of my favorite courses to teach. So I have this pattern here to reflect that. This was constructed using Gaussian primes, which are the primes in the complex numbers. So what I did to construct this was to plot a disk at all the locations of Gaussian primes in a certain region of the complex plane. And then I used the edge detection feature in Photoshop to sort of pull out that boundary, and I got that pattern. No doubt the worst part of my job is grading. Some of the patterns reflect a tendency that I have to what I call procrastinate. So maybe you guys understand this pretty well. This is when you get involved in some activity just to avoid grading. You know, the activity might be answering email or cleaning toilets. Whatever it happens to be, it's just you cannot grade at that point in time. At this particular time when I created these 3 patterns that I'm highlighting here, I was trying to avoid a stack of linear algebra exams. And so I decided it was necessary that I visualize the divergence of a vector field. And I actually spoke about this a couple years ago at Bridges, so I'll just give a little condensed version of that talk. But these 3 images, which appear in the piece, came from trying to visualize the divergence of a vector field. In particular, I was asking the question, can I visualize sources in a vector field? And so let's just recall the definition. The divergence of a vector field is a scalar quantity. And that scalar quantity measures the tendency of a vector field to diverge from a point. If the vector field is 2-dimensional, meaning you have a vector field in the plane, we have 2 coordinate functions, p of xy and q of xy, you can compute the divergence by computing the partial derivatives, dp dx and dp dy, and then you add them together, and that gives you the divergence of the vector field at the point xy. It might be helpful to think of the vector field as a velocity field of fluid flow. And if you do that, in this case, you might think of a source as being a source of new fluid. If there's more flow out, like for example at the origin, the vectors are emanating outward, you can think of that as a spring or a source of new fluid in the fluid flow. Then the divergence is positive there, right? The positive divergence indicates that. And so in this particular case, if you go ahead and compute the divergence, you get a constant value of 2, meaning that the divergence is positive everywhere, so you get a source everywhere in the plane. Now, geometrically, that's pretty clear at the origin. away from the origin, what we like to do, at least I tell the students, is take a itty-bitty circle around a point, and then you sort of say, okay, is measuring the flow, total flow out versus in. The total flow out outweighs the total flow in, then you have a source of fluid inside of there. Okay? So every point in this case, you'd get a source of new fluid. If you take this vector field and multiply by a negative, that's going to change the order or the direction of those arrows. Now they all point inward, and every point is a sink, meaning that you have a sink of, say, old fluid. Okay, now these two examples, which are pretty common when you first introduce the idea of divergence in say, a calculus course, it's easy to visualize these. If the vector fields get a bit more complicated, not so much. Okay, so let's consider this one here. If you look, there's certain places where it's kind of clear, like at the origin, the vectors are pointing outward, you'd have a source there, and the corners, they're also emanating outward. But at other places where the vectors change direction and length quickly, it's not so easy to determine where sources might be and where sinks might be. So what I decided to do is to try to visualize this by coloring points in the plane, white if it's a source, meaning the divergence is positive, and black if it's a sink. And I found that in certain cases you get some nice patterns, like this one here gives you this pattern with some nice reflective and rotational symmetries. And if you zoom out, you'll see that you also get some nice translational symmetries. You get a wallpaper pattern. So after playing with these for a while, I pretty quickly honed in on vector fields of this particular form, where the the I component is a product of sine and cosine, and J component also a product of sine and cosine. And that's the case with all three of these patterns that appear in my piece. And I have the parameters beneath that define the particular vector field that produced it. The question is, well, why did I hone on these ones? Well, once you compute the divergence, it becomes kind of clear. So if you compute the divergence and compute the two partials, what you get are two terms, both that involve cosine only. Okay, now why is that relevant? Well, the cosine function is a periodic function. And so what we have is then a periodicity that will occur not only in the x direction, but also in the y direction. So what that's going to give me is the translational symmetries in the x and y directions, which gives me the wallpaper patterns that I wanted. So I was after wallpaper patterns. That gives me the nice symmetries that I want. And so here are the fundamental regions for these particular wallpaper patterns. Additionally, the cosine function is an even function, which means that I can replace x with negative x, and I'll still get the same value for the divergence. I can also replace y with minus y, and once again, I'll get the same value for the divergence. And what that means is that I'm going to get nice reflective symmetries as well. Okay, so I'm going to get vertical and horizontal reflections in my piece. And finally, what I can do is replace both x and y with minus x minus y. Get the same value in the divergence, and what that means is that I'm going to always have a rotational symmetry by 180 degrees in these patterns. So I have lots of symmetries, and if certain other properties are satisfied, so for example, if A equals C and B equals D, or A equals B and C equals D, then I also will get a 90-degree rotational symmetry, which is what I have in this particular case. Okay, so depending on the values of these parameters, you could get additional symmetries. Here's a sampling of some of the patterns that we played with. I just think they're incredibly beautiful. They remind me of some of the prints or patterns you'll see in African textiles and in some of the weavings. And what we did at Bridges, so this was a colleague, Marie Snipes, who was also at Kenya with me. The two of us were in Seoul. And what we did was, she was particularly interested in these four patterns, and patterns like them. So you notice they have vertical and horizontal lines running through them. Those are going to be lines where the divergence is exactly equal to 0, because you can see they sort of border between black and white regions. So we called those lines of incompression. And also you can see that in a couple other of these cases, there are diagonal lines that run through them. Same kind of idea. There's going to be lines of incompression. And so we were trying to identify in our last Bridges talk, which patterns or when will we get these lines and when we won't. Okay, so that was, if you go back to the last Bridges proceedings, you'll see a paper about that. My colleague Marie was also intrigued by the fact that many of our patterns reminded her of these patterns known as Chladni patterns. And if you're not familiar with those, Chladni was a a physicist who was also a musician. He was interested in acoustics. And the idea is that you vibrate a square piece of metal, and actually it doesn't have to be a square, and it doesn't even have to be metal. It could be, say, a violin or something. At different frequencies, you sprinkle sand on there, and when this plate vibrates at a particular frequency, the sand is going to be pushed to certain areas on that plate that don't move, and the result is some nice geometric patterns. There's going to be a talk about this, I guess, on Thursday afternoon. So if you want to learn more about Chladni patterns, you can go to this talk on Thursday afternoon. In any case, Marie and I got a colleague of ours in physics to help us play with Chladni patterns, and these are some of the patterns that we produced. And indeed, some of them do look a lot like these divergence patterns. Right? So this was actually the inspiration for one of the patterns that appear in my piece, which I think of as like a mathematical eye. It looks a little bit like an eye there. And the vectors, the normal vectors emanating outward are like eyelashes, I guess, in my mathematical eye. I just think this, again, these Chladni patterns are just beautiful. Okay, next what I want to do is move on and talk about 3 more patterns, the ones that I've highlighted here. These hold special importance to me because they came as a result of some undergraduate research that I did at Kenyon with probably like 8 students over the course of about 10 years. Getting a better look at this. The one on the left you're probably very familiar with. It's the famous von Koch curve, or the Koch snowflake. And the 2 images on the right are patterns that are closely related to what's known as the Toohey-Morse sequence. So I'm going to say a bit about the Toohey-Morse sequence in my talk. Okay, but first the Koch snowflake. Well, Koch snowflake is a very famous fractal object. It's defined iteratively, starting with an equilateral triangle. And the idea is that with each iteration, we take each edge in the figure and replace it with what you would get if you take that edge, remove the middle third, and then add 2 line segments that would be the 2 other sides of the equilateral triangle, with base equal to that removed edge. Right? So with this first iteration, we end up with 12 edges, and then for each of those 12 edges, you apply the same rule. Right? And we keep doing this. Right, until we can't really see any more change in resolution, although the Koch snowflake is what you would get if you were to do this indefinitely. And if you look closely at my art piece, you'll see that it's that 4th iterate that appears, and I've repeated it twice just to make the pattern more interesting. Okay, so now the Toohey-Morse sequence. So I want to introduce the Toohey-Morse sequence to you by posing a question. So the question is, here's a sequence of tiles. You might think of this as maybe tiling a border that goes around your coffee room in your department lounge, coffee lounge. And the question is, what will the next 2 tiles be in this tiling pattern? Okay, so I'll let you think about that a little bit. So what should be the next 2 tiles?
Black and white.
Black and then white, okay? That's right. So it turns out that this tiling pattern was constructed by contrarians. You might think of it as maybe a faculty committee tried to construct this. The first faculty member puts down a white tile. The second faculty member says, oh, no, that's all wrong. It's not white. We should have black. And the third faculty member says, oh, white, black, that's wrong. It should be black, white. And the 4th person comes along and says, white, black, white, that's wrong. It needs to be black, white, black, and so on. And if you do that, you'll see that the last 2 tiles should indeed be black, white. Suppose now that same faculty committee wants to tile the floor of the coffee room. How might they do that? Well, the first faculty member puts down a white tile. The next faculty member says, no, that's not right. I'll put down a black one. The third faculty member says, oh, no, we don't want white, black. I'm going to put black, white below it. And now you can think of that as a tile in and of itself, and you can play the same game with that tile. So with that tile, the next person comes along and says, white, black, white. No, that's not right. It should be black, white, black. And then the same, similarly beneath into the bottom right corner, and I can now treat that, with the resulting tile, as a single tile and play the same game with that tile. And I'll get this, do it once more, and there's my tiling of the coffee room. Okay. This appears in my piece, but I've transformed it. I've transformed it to make it have a bit of a landscape. The hope was that I would be inviting my reader, I guess they're not reader, viewer, inviting the viewer into my mathematical world. More formally, we define the Toohey-Morse sequence iteratively as a 2-symbol sequence using 0s and 1s. So the initial string that we start with is x0 equals 0. And then with each new iteration, we define the new iteration by way of concatenation. Okay, so x sub n plus 1 depends on x sub n. By concatenating xn with xn bar, or you should think of the xn bar as the contrary map. So what that means is any symbol 0 that appears in xn should now become 1. If it's a 0, it becomes a 1 in xn bar, and if it's a 1, it becomes a 0. So we just do that change. Okay, change all 0s to 1s and all 1s to 0s. So with that in mind, x1 is x0 bar, which will be 0, 1, right? Because the negation of 0 is 1. And similarly, x2 will be x1 bar, which will be 0, 1, 1, 0. And we can keep playing that game. And if you kept doing it indefinitely, you would get what's known as the Tuohy-Morse sequence. Okay, like the number pi, the Tuohy-Morse sequence is a ubiquitous object in mathematics. It sort of pops up in unexpected places. Many, many interesting properties. So for example, the Tuohy-Morse sequence is what's known as cube-free, meaning that there is no occurrence of a substring anywhere within your sequence of the form www, where w is a word constructed from 0s and 1s. Okay? If you look, there are plenty of squares, right? Lots and lots of squares, right? No cubes anywhere. The sequence is not periodic, but there is a lot of repetition in the sequence. So for example, if you look at the first 4 symbols, 0, 1, 1, 0, in the first 28 symbol, that word of length 4 appears 5 times. Okay, and I just sort of picked that randomly, but we can make this repetition more rigorous with another definition. So the sequence is also what's known as recurrent, which means that if you pick any word anywhere in the sequence, let's call that word w, then there's going to exist a finite length, which I call L sub w, such that any substring anywhere in the sequence of length L sub w is guaranteed to contain that word w. Okay, with the simple case, what if my word is just the single element 1? Then it turns out that L sub w will be 3 in this case, because as we said before, this sequence is cube-free, which means if I take a substring of length 3, there has to be a 1 in there. You can't have 3 zeros, because then I'd have a cube. Right? So L sub 1 in this case will be 3. And if I look at something a little more complicated, like 1, 1, 0, 1, and you can see I have 2 occurrences highlighted here, and then I have a window here that's of length 14. That blue window contains no occurrence of w, and so in this case what we know is that L sub w has to be greater than 14. Right? But we're guaranteed that there will exist an L sub w that of some length that's guaranteed. If you pick any string anywhere in that sequence of that length, you're guaranteed to contain that word 1101. So this really does have a lot of repetition in it. But in my mind, the coolest property of all is the self-similarity that this sequence exhibits. And so to let you know what I mean about that, take this sequence and break it up into blocks of size 2. So there we have it, blocks of size 2. And then we're going to define a replacement rule. The replacement rule is to take 0, 1 wherever it occurs and replace it with a 0. And whenever you see a 1, 0, replace that 1, 0 with a 1. Okay, so if the first block, 0, 1, is replaced with a 0, the second block, 1, 0, is replaced with a 1. The next one, 1, 0, replaced with a 1. And then 0, 1, 0, and I keep going. And then I smush my symbols together, and I get my Tuohy-Morse sequence back again. Pretty cool, isn't it? But it gets better. Because now what I can do is I can take this sequence and I can break it up into blocks of length 4. There you have it. And then what I'm going to do is I'm going to take every occurrence of 0, 1, 1, 0 and replace it with a 0, and every occurrence of 1, 0, 0, 1 and replace it with a 1. So 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0. Smush the symbols together, I get my Tuohy-Morse sequence back again. In fact, I can take this sequence and break it up into blocks of size 2 to any power, define the same kind of replacement rule, and I'll always get the Tuohy-Morse sequence back. Right? That Tuohy-Morse sequence will exhibit that self-similarity on that particular scale, 2 to any power. This is a very, very cool sequence. Okay. Okay, so it's called the Tuohy-Morse sequence, but in fact it was defined, or I shouldn't say it was defined, it was discovered earlier by a French mathematician by the name of Eugene Pruitt. He was trying to understand a problem from number theory, which is now known as the Pruitt-Terry-Escott problem. And he didn't actually define the sequence explicitly, which is probably why the sequence doesn't bear his name. He sort of stumbled upon it while trying to construct a solution. This is a little bit tangential to my talk, but I like the problem because I like number theory, and since I'm the speaker, I thought we could talk about it. Okay. So here's the problem. The problem is you start with a couple of integers. One is positive, that's n, and the other one's non-negative, that's k. And then we're going to take a set that consists of n consecutive integers from 0 to n minus 1. Now, the more general problem, you don't have to have consecutive integers. The set could just be any set of non-negative integers, okay, of some finite set. It should be finite set. But in this case, just to make it simpler for the sake of this talk, I'm going to just look at sets that have consecutive integers in it from 0 to n minus 1. And then the question is, can I take that set and partition it into two sets A and B, such that when I sum up the elements in each of the two sets A and B, I get the same value. When I sum the squares, I get the same value. And when I sum up all the powers up till that power k, I'm always going to get the same value. Right? That's what the Terry-Escott, Pruitt-Terry-Escott problem says. So let's look at an example. Suppose n is 8. And S will be the set of integers from 0 to 7. And I'm going to define A to be the set 0, 3, 5, 6, and B to be the set 1, 2, 4, 7. And then I'm going to add up all those elements in each of the two sets A and B. And if I do that, I get 14 in both cases, right? So, okay, so it works for I equal 1. Now what I'm going to do is add up the squares in those two sets. And what do I get in both cases? 70. Right? So this particular construction of A and B, this partition of the set S, will give me a solution to the Pruitt-Terry-Escott problem when k is 2. Right? If I now try the power 3, it doesn't work. So this is going to be a solution where k is equal to 2. And my capital N in this case is 8, which is 2 cubed. Okay? So if you're wondering how might you actually construct these two sets A and B, well, I give you a hint. I list the 2E sequence right underneath there, and do you notice anything? If you notice A, it's going to be the elements that are assigned to the 0 in the sequence, and then B is coming from the elements assigned to 1. Right? So that 2E sequence is sort of saying, do I put it in A or do I not put it in A? Okay? And if you want to say, okay, can I generalize this to get solutions for other sets in a similar way? It turns out that you can, as long as your set S has order 2 to some power. Again, the powers of 2 are coming to play. And so 2 to some power, in this case, is 2 cubed, but 2 to some other power, and then the k will be 1 less than the exponent on that power. Right? So if I could play the same game if I took n to be 32, for example. But you can push the solution a bit further. In fact, it'll work for any multiple of a power of 2. Okay? So this is pretty much how Pruitt stumbled across this sequence, just trying to solve this problem and being able to construct a solution in a particular case. The sequence wasn't defined explicitly until the early 1900s when Axel Tui was interested in avoidable patterns in sequences of symbols. And he proved that the sequence is overlap-free, which means there's no word anywhere in the sequence of the form WU, WU, W. Okay? In the English language, a word that has that form would be the word alfalfa. Okay, so alfalfa has that overlap in it. But you won't find anything like that in the Tui-Morse sequence. That's what Tui proved. And in the early 20s, Marston Morris brought this sequence to worldwide attention because, through his work in differential geometry. He was interested in the aperiodicity of the sequence. Finally, in 1929, Dutch mathematician and world chess champion discovered the sequence again when he was interested in constructing infinitely long games in chess under certain draw rules. So he used the Tui-Morse sequence to construct an infinitely long game. And apparently, these were the rules that were in place at the time. Okay, so I was reading about this sequence and all of its interesting properties, and I just thought this is really intriguing. I want to be able to visualize the sequence. And so I was trying to think how I might visualize this sequence, and immediately I thought about the turtle graphics, because turtle graphics provides an easy way of taking a sequence of symbols and converting them into a geometric object. So if you weren't alive in the mid-'80s, then maybe you haven't heard of turtle graphics, but I can describe it to you pretty quickly. The idea is that you have a turtle in the plane, and the turtle has a pen. And by giving the turtle commands about where to walk and maybe to turn and so on, that turtle can then trace out a figure. And so you can, by having a sequence of turtle commands, you can describe a geometric figure in the plane. So for example, if you want to describe a square, you might say, okay, turtle, move forward 1 unit, turn counterclockwise 90 degrees, and move forward again 1 unit, and keep doing that 4 times, and you'll describe your square. Okay? So it's a very easy way of constructing geometric figures, and it was really popular in the 80s because it was really accessible to young children, and it introduced them to programming in a very nice way. So this came out of MIT. All right, so I was thinking I have a 2-symbol sequence, and with the 2E sequence, so I want 2 turtle commands. And I use the 2 turtle commands F and L. F represents 1 forward motion, or a forward motion by 1 unit. And left is a 60-degree rotation in a counterclockwise direction. And then if I just let F play the role of 0 in the 2E sequence, and L play the role of the symbol 1, what I'll get is I'll produce a bunch of 2E turtle programs that I can then visualize because I can look at the drawing that the turtle has created. Okay, so that's what I did. So what I call TM0, that's the 2E turtle program, the initial one, which is F. And when I apply that contrary map for TM1, I get FL, and TM2 will be FLLF, et cetera, et cetera. One thing that I want to note here, because it's going to be important in a minute, is that another property of the 2E sequence is that the even iterates are palindromes. Okay? So even iterates are palindromes. Look at TM2, FLLF, and then TM4. You can see that reflective symmetry in there. That's going to have some relevance. All right, and now I want to draw these things. So if I just start with TM4, for example, we're going to assume that the turtle starts with its heading upward. And then I'm going to look at the first 4 commands, FLLF. And the turtle's then going to draw 2 edges corresponding to the 2 F's in that word. Moves forward 1 unit, rotates twice 60 degrees before it writes down or draws, I guess, the next edge. And then you can see that final, I guess, the heading here is the heading that the turtle has after completing the first 4 commands, right? And I can do the next 4 commands, and I'm going to get 2 more edges coming from the FF there. And then that's the first half of TM4. Now what I'm going to do is make use of the fact that TM4 is an even iterate, and so I'm going to have a reflective symmetry. So I can use that, right? Because I have a palindrome, what that means geometrically is that the turtle trajectory is going to have a bilateral symmetry in this. So I'm just going to take that trajectory that I have and flip it about the axis that goes from the starting position of the turtle and then to where it was. And I get something that looks like a pointy heart. Okay, so TM4, when I visualize it, looks like this. Now I'm going to play the same game with TM5, 6, and 7. So there's TM4, TM5. I lose my bilateral symmetry because it's an odd iterate. There's an even iterate. I get my bilateral symmetry back again. There's TM7, TM10. And if you look carefully now, you'll see that TM10 is the pattern that appears in my piece. Okay, it's that 10th iterate. If I go out to just the 14th iterate, you can see it's pretty convincing that these turtle trajectories are converging onto a third of the cock snowflake. Okay? So when I saw that, I was just like, whoa, I got goosebumps. This is really cool. I had no idea this was going to happen. But I guess, you have self-similarity in these fractal curves, so it's kind of nice that I could see it this way. And I have to say, too, that, how would I know to put in 60 degrees? I didn't. Initially, I put in like 90 degrees, and I tried different things, and then this is what I eventually stumbled on. Okay? And then I enlisted the help of an undergraduate by the name of Jun Ma to formalize this result. And this is the theorem we ultimately proved, which appeared a year later. So we worked on it in the summer of 2005, and it appeared in 2006. So I won't go through all the details, but I'll just sort of unpack the notation for you. What we did was we said, okay, let script K be 1/3 of the cock snowflake. And then I already said that the TM sub 2n, those are the even iterates, the 2E Morse turtle programs, right? The even iterates are the ones that converge, not the odd. And then this K map here, what this does, this I found in literature, I found it is due to decking. It was a way of realizing a sequence of symbols as a polygon in the plane. So this was exactly the map I needed. So I was very happy to see this. And that's what that represents. Again, I won't go into all the details, but just think of it as a way of just realizing this sequence of symbols as a geometric polygon in the plane. And then this S sub n is scaling my trajectories down, because the turtles always grow in the same distance, right? The forward motion by 1 unit, that 1 unit is always the same distance. So with each iterate, I'm getting a bigger and bigger and bigger trajectory. So to get the convergence, I have to scale it down by the appropriate amount. And that's what that S sub n does. Okay, and then we use the Hausdorff metric to be able to define the distance between these compact figures in the plane, which is the typical kind of metric you use when you're dealing with fractals. Okay, so that was the result. Okay, so now I'm going to turn our attention to this second portion of my talk, which is the shorter portion, so you don't have to take what we did just now and double it. Don't worry, you'll have time to eat lunch. And we're going to turn our attention to the formal definition. And as I said before, it's that formal definition that defines the composition of my piece. So what we're going to see is that these white floating surfaces here are projections of the real projective plane into Euclidean 3 space. Okay? And in fact, there are different snapshots of a surface known as the Boy surface, named after Werner Boy, who was a German mathematician. Werner Boy discovered this surface in 1901 when his thesis advisor, David Hilbert, asked him to prove that it's impossible to immerse the projective plane into Euclidean 3 space. Okay? So David Hilbert was wrong, and the Boy surface became the focus of Werner Boy's doctoral dissertation. Formally, an immersion between two differential manifolds, M and N, is a differentiable function from M to N, which I call F, whose derivative is everywhere injective. Okay? So when I say differentiable manifolds here, just think of, okay, I have a space that locally looks like Euclidean space, and I can do calculus on it. Okay? So I'll just wave my hands. And I want to emphasize that it's the derivative that's injective, not the function itself. If the function itself were injective, then that function would be an embedding. Okay, so we're not looking at embeddings, although it could be an embedding, but we're saying that the derivative is what's injective. Okay. Alternatively, you could also define an immersion to be a local embedding. So it turns out to be equivalent. And what I mean by that is that for any point x in the space M, there exists a neighborhood U about x and M, such that when you restrict the function f to that neighborhood U, you get an embedding. Okay? So I'm going to get an embedding locally on that neighborhood around x. Okay? Now, I'm eventually going to talk about the Boy surface, but I want to start at a lower dimension because, in fact, my piece features an immersion of a one-dimensional differentiable manifold into Euclidean space, the plane. And so what I have here is this closed curve with two intersections, and that represents an immersion of the circle into Euclidean 2 space. Okay? It's not an embedding because there are two places at which this curve intersects itself, but it turns out that it is an immersion, meaning that the derivative is going to be injective everywhere. And that might seem kind of confusing because you might say, well, wait a minute, there's two tangent lines, assigned to the point where the intersection occurs, but we can elaborate a bit here. So to elaborate, I have some pictures. What you want to see is that locally there is a well-defined tangent line at each of those points. So in particular, observe at the point x there, it maps to one of the self-intersection points, which I have labeled as f of x. And you might imagine that the neighborhood u of x, as illustrated on the left, will embed into R2 with image f of u, the neighborhood of f of x, which is pictured on the right. Okay? And if you restrict f to the neighborhood u, that's going to result in a single tangent line that runs right along the red portion of that curve. Right? And in a similar way, you can consider a point y, which I have pictured on the left, and there's going to exist this neighborhood v about y, such that if you take f and restrict it to v, then v will be embedded into the closed curve or into the plane on the right, and you'll have a well-defined tangent line that runs along that blue portion of the curve. Okay? So locally, you have this well-defined single tangent line, and in this way, this is what we mean by this derivative being injective. If you know some knot theory and you've seen some knot diagrams, and maybe you're familiar with immersions already of the circle into the plane, because that's what these knot diagrams really are. There are immersions of the circle into the plane, except you have some additional information, because at each crossing you have this information that says which strand is on top and which strand is on the bottom. Right? So these knot diagrams are immersions of the circle and plane with extra information that says which strand is on top and which strand is on the bottom. All right, so now I'm ready to move back up a dimension and talk about the immersion of the real projective plane into Euclidean 3 space. And to this end, I want to recall what the definition of real projective plane is. So we denote it by RP2. It's defined to be the set of all lines in three-dimensional space that pass through the origin. So points in this space are lines, right? And sometimes it might be hard to envision lines as points, but you just have to keep in mind, I guess, the motivation of this space. It lives in art, which we all know and love, right? And particular linear perspective, right? So the way to think about this is that lines going through the origin can be interpreted as lines of sight that run through the artist's eye. Right? So think of the origin as the artist's eye. So this is a one-eyed artist. The picture plane, or the canvas, is a representation of a portion of that real projective plane. Right? It's only going to capture the lines of sight of the artist that intersect the canvas. It's not going to be able to capture all of the lines, just the ones that intersect that plane, or the canvas. Okay? If you want a representation of all of projective space, there are many different models out there. Okay? One of them is the one I'm going to talk about here. Starts with the unit sphere, and so I have a picture of the unit sphere in blue. Notice that every line that goes through the origin is going to intersect that unit sphere in two different places, at the point P equals x, y, z, and also at the point which is at the sort of diametrically opposite point, which will be minus x minus y minus z, right? So it might make sense then to define the real projective plane, to come up with this model by taking the quotient space of that unit sphere and identifying every x, y, z with its antipodal partner, negative x, negative y, negative z. And that's what we do. But then what happens is that you have two different points on your sphere that represent the same point in real projective space. And that's redundant, and we don't like redundancy in mathematics. So instead what we're going to do is say, okay, well, let's use the hemisphere instead. I'm using the upper hemisphere, but you can use the lower hemisphere. Anyone will do. And then we want to include the points on the equator as well. But when we do that, we have to still identify the antipodal points. So imagine now that every point on the upper half of that sphere represents a unique point in projective space. And then I have to somehow realize this space to get the real projective plane by identifying antipodal points that live on the equator. Okay, and when I do that, I get my hemisphere model. So when I refer to the hemisphere model, this is what I'm talking about. Now, when I first was introduced to the real projective plane in graduate school, this was in a topology course, I was taught that the real projective plane comes from the square. Okay, so I didn't learn about the really cool interpretation of the lines of sight through the artist's eye and all this stuff. It's just like the real projective plane is a square. Here it is. You identify the bottom edge with the top edge with a twist, and the left edge and the right edge with a twist. And if you carry through or it's not mine, it's been out there, right? This upper hemispherical model through, you can sort of see these are the same thing. In fact, with this square model, what you see is that my artwork actually resides on the real projective plane. In particular, if you look at the curves that are exiting the bottom edge here, they match up precisely with the twist of the ones exiting the top. And I can emphasize that by repeating the top down below with a twist. So there it is, and there's that curve that matches up. And similarly, the ones exiting the left line up perfectly with the twist of those exiting the right. And in this way, in fact, I lied earlier when I said that the circle was immersed in the plane, because in fact I have two circles immersed in the real projective plane in my piece. All right, that's really what's going on. So I have two circles immersed into RP2 here. Going back to realizing the boy surface now, or that hemisphere, and I want to try to construct some object in 3 space that represents it. There are several well-known ways to do this, and 2 of them are pictured here, the cross-cap disk and the Roman surface. Turns out that neither of these are immersions, right? So the cross-cap disk has what are known as what's known as pinch points, and there are 2 of them for the cross-cap disk. They reside at the endpoints of the line of intersection. These are places where a tangent line just doesn't exist, or a tangent plane doesn't exist, and so the function is not, or the surface is not differentiable. And then for the Roman surface, there are actually 6 pinch points. You can only see 3 of them, but keep in mind that this surface is highly symmetrical. And to really picture it, you might want to think about this as living or being circumscribed inside of a tetrahedron that has edges of equal length. The pinch points would reside at the midpoints of each of those 6 edges. So there's 6 of them, and they're going to reside at those midpoints of each of the 6 edges. If you zoom in on these pinch points, you'll see what looks like what I have circled there on this famous non-singularity known as the Whitney umbrella. At the very top of the handle, that's where the immersion fails, right? That's where you don't have the nice tangent plane, okay? So these 2 cases are very famous realizations of the real projective plane in 3-dimensional space, but they're not immersions because you don't have this nice smooth behavior. The Boy's surface, on the other hand, has no pinch points, and it's differentiable everywhere, right? And in this way, you should think of the Boy's surface as being sort of less degenerate than the other 2. Okay, and you'll see this image then on the lower right-hand corner of my piece. Okay, a little history about this surface. I already said that Werner Boy was the person who discovered it. It's interesting to note that he did not discover an algebraic way of constructing this. Rather, he sort of discovered it purely topologically. He drew pictures. So it took another, over 70 years before French mathematician Bernard Maurant discovered the first algebraic parameterization of the surface, right? How you can actually construct it algebraically. And this is a picture of Maurant, which I absolutely love, because in reading this, I don't know, I was really excited to learn that he was a blind mathematician, had been blind since age 6, and yet he was somehow able to see how to visualize, how to construct this surface in a very explicit way, right? Very interesting. And he's holding this model here, which was, I think, it had to have been constructed in, say, the early 90s. And so it was constructed not by 3D printing as we know and love today, where we extrude plastic, but rather using the technique of stereolithography, where you have a liquid polymer and a laser beam that's focused on the areas that you want to harden. And when the laser beam makes contact with this liquid polymer, it hardens, and then it's constructed in sort of layer by layer fashion. So I don't know if you can tell with this model, but there are cutouts in the model so that Maurant can actually touch the places where the intersections are happening. You could see the smile on his face. I just think this is a great picture. But I didn't use his parameterization to visualize the surface. I actually used the parameterization of his student, Francois Apery. And I'll show you what the parameterization looks like. It's somewhat ugly. But it's, you can find it online, you can play with it. I rendered this in Mathematica and got some really nice results, and so you can see it very nicely here. What the idea is that you start with this hemispherical model, and then the equator gets squashed to look triangular in shape, and that's going to give you this 3-fold symmetry. So what happens is at each stage along the way, that 3-fold symmetry is maintained as we want to identify the antipodal points. So you can see that we just sort of actually it's hard to see, especially when they start to cross. Just keep in mind that you're seeing one lobe here, but the same thing is sort of happening at each lobe. And that's going to give me the image that's on the lower right. Okay, the surface that's floating on the top there, that's actually a reverse view of Apery's parameterization. So if you were to come from it back end, this is supposed to represent that. The surface that I have floating off the left side here, this is based on another parameterization that was constructed by a couple of mathematicians independently, but right about the same time. So Robert Bryant, who is currently the president of the American Mathematical Society, he found a whole family of parameterizations of the Boy's surface. This was in the mid-'80s. And then Rob Kussner also found a parameterization, but it turned out to be a special case of Bryant's, and they did this right about the same time. And their parameterization was also used as the basis for the model of the sculpture that graces the grounds at the Math Research Institute in Oberwolfach. So this is the Boy's surface there. The steel strips in this piece, you can see these steel strips coming down. This is a representation of the polar grid. of a polar grid under the parameterization. Okay, so this is, again, coming from Kussner and Bryant's parameterization. Okay, I've spoken about most of the patterns in the work, but, well, maybe not most. I mean, I just pretty much scratched the surface. I could write a whole book about this single artwork. I mean, there's just so much mathematics in here. But I won't go on and on at this point. Rather, what I'll just do is answer the question, why am I focusing on immersion so much? Well, I kind of like the notion of immersion for a couple of reasons. One is I feel like sometimes we just have to escape reality and immerse into our own world so we can, actually have meaningful thought. And, like sometimes my blood pressure raises and I need to lower it. I'm just going to escape into mathematics. It's a great place to go. There's sanity. There's civility in mathematics. It's rational. Okay? The second one is that I'm a huge Cavs fan. Okay? Huge Cavs fan. LeBron James grew up in Akron, Ohio, which is 20 minutes from my hometown of Ravenna. So I'm a huge LeBron fan as well. And I'm a huge fan of the Cleveland Cavs slogan, all in. I mean, because in those two short words captures the notion of immersion very, very well. And I think that his LeBron and the Cavs as a whole, their all-in mentality has propelled their success. And so I think the idea of immersion is nice too because it propels our success as well by getting immersed in something. And so this brings me to my last slide, which is about Reza, because I think he was really good in terms of immersion as well. I would say that he immersed himself in the creation of an organization, that being Bridges, and a community that then encouraged meaningful immersion from all of us. And similar to LeBron, I guess, in basketball, who makes the people around him play better at a higher level, I feel like Reza did the same thing, right? So he encouraged his community in this organization that allowed people around him to grow in meaningful ways. So with that, I will close my talk, and thank you for listening. Maybe a couple of questions.
There are any? Yes.
So the last voice surface you showed didn't look so much like the voice surface earlier. So is it another immersion of the real projective plane, or is it homotopic to voice surface?
That's right. It's homotopic to voice surface. It's another parameterization, exactly. And they have different looks to them, right? Yeah. Mm-hmm.
But are there other? Is every immersion actually homotopic to voice
Yes.
surface?
Yes. Yeah. Mm-hmm. Any other questions?
Even like
Okay.
if you twist, because it has a flipped version, no?
Well, you can't introduce kinks, certainly, right?
I'm saying that isn't there a, okay, it doesn't matter.
Okay.
Let's have lunch.
Yeah.
Okay. Let's thank our
Thank
speaker
you.
again.